Hello there, and welcome to How to Interpret My Plasmidsaurus Sequencing Results. Today we're going to walk through how to interpret your plasmid results directly on the Plasmidsaurus website. Once your results are ready, which can be as soon as a few hours after you've dropped your samples off, you're going to receive a results email that looks a little bit like this one. On this page you can see the summary report, which is a quick snapshot of the linearized plasmid maps of all of the samples in your experiment so that you can quickly see how it went. If I click on this View Results button, it will take me to the website order page. Now, when I look at this summary table, you can see on the right that I've uploaded references. That can be done by clicking here and then clicking the Upload Files button, or simply dragging and dropping into the box. The supported file types are Fasta, GenBank, and Snapgene. Now, the great thing about uploading a reference is that we will automatically align your consensus sequence to that reference. And you can see then that we will color them based on how well it aligns. If it matches perfectly, we denote that with this happy looking Dino. If you have one or more mismatches, you get the dreaded chicken. And we also have this egg that denotes a likely match, and there'll be more on that in just a moment. Now you can see everything is interactive and clickable. I can see the annotations, and if I click on this sample, it will take me directly to it. Now we've got this perfect match, and you can see that if I kind of zoom around, we've got the per base view that really dives into every single base and how well it matches, as well as the amino acid prediction and the read support at each position. So here you can see the consensus called a T, and that is because 100% of the reads called a T at this position. Sometimes you will see some variance. So here we try and highlight it, and if I look at the per base information, you can see that almost 80% of the reads called a C at this position, but that 22% of the reads called a T at this position. That may be biologically relevant to your experiment, and so we'll highlight that to make it clear for you. Now if I scroll down to tube number 2, this was the likely match to reference, and you could be forgiven for wondering what on earth a likely match could be. Well, Oxford Nanopore sequencing has got a couple of types of systematic error. We've written about these in more detail in this blog post, which we will link down below. If I click on the mismatch, we can see a little bit more about what's going on. To make it a little clearer, I'm going to highlight this short sequence here, which some of you will know. This CCAGG, this is the canonical E. coli methyltransferase motif, which means that this internal cytosine right here is frequently methylated. So instead of being canonical cytosine, it is a 5-methyl cytosine. Now, of course, that methyl group means that it's got a different shape and size. As it moves through the pore, the base caller registers that different size, and that can cause it to throw this systematic error. So if I look at the per base information, 100% of the time we have a T called. But we know more than the base callers. We know that this type of methylation motif, when it is methylated, can throw off the base caller in that systematic fashion. And so that's why we highlight it as a likely match. And so this means that the mismatches match the pattern of common sequencing artifacts. Now if I scroll to tube number 3, we can see, we've got a deletion. Again, if I hover over, it's going to show me we've got a 1.5 kb deletion. If I click on it, it will jump to it. And I can see that just before we've got perfect match, and just after we've got perfect match. But we are completely missing this gene, so that is a good thing to know. If I scroll to tube number 4, we've got a different issue. So again, if I click on it, it will take me right to it. And you can see that we have got, as it highlighted, a deletion of one base pair. It's matching before, it's matching afterwards, but we're missing this A. And you can also see that this has caused a frame shift. And so in the reference, you can see that we keep making protein. However, this frame shift has introduced an early stop codon. So we know that in the sample that you sent, this protein is going to be truncated. And this is a great example of why we say you should sequence everything, because knowing this ahead of time will prevent you spending hours, days, months troubleshooting experiments that were never going to work. You drop this sample in the Dropbox, and by the time you come into the lab the next day, you can click this results email and see that this plasmid is not going to work. You should choose a different one or remake it, whatever it is you need to do, and that will save you a lot of time troubleshooting failed experiments. Lastly, I want to show you this virtual gel feature that we have. So this is, as you can see, designed to look like gel electrophoresis. And the brightness of the band is proportional to the number of reads at that length. So this is a great way of comparing lengths between samples, but you can also see within a sample that here I have got a second plasmid. It looks to be very close to double the length, so this is probably a concatemer. And so this is a good place to look for overall QC. Okay, well, thank you so much for watching. I will see you next time.